Welcome back to the last part on password security. We have discussed how users should choose the password, or how they should not choose the password. We talked about how the password is transmitted from the user to the verifier. And now we have to talk about how the password is stored on the verifier side, and therefore how easy or hard it is for the adversary to steal the password from the verifier side. So let's imagine that you're logging in on your email service provider, you're inputting your password on your machine, the password is being transmitted maybe via encrypted communication to the server. Now the server has to check that the password you input is correct. So the most easy way of doing this, the trivial way of doing this, which had been the common way of doing this, unfortunately, for a long time on many or on many devices, is to simply store the password on both the server side and on the client side, and then to store the password on the server side, so that when the user input the password, the server can check that the new password that arrives it's equal to the password which was stored. So you, for instance, keep the password in a database, and then when the new password arrives, you simply do an equality check between the string you receive and the string you have stored, and then you check whether they're the same. So this is considered to be very insecure, and it's definitely something you should not do, because it's not very hard to steal the passwords from servers. Also, therefore, the servers or the verifier side should not store the password itself, but should store some function of the password. So in particular, the servers typically store the hash of the password. We already discussed hash functions in the chapter on authenticity. If you need a refresher on that, please go back. But remember, the idea of a hash function is a function that takes an input of any size, hashes it down to an input of fixed size, an output of fixed size. The hash function, it's easy to compute, so it's easy to compute the password, the function in the forward way. So given the password, it's easy to compute the hash of the password, but it's hard to invert. That therefore it's called a one-way function, meaning that given the output of the function on an input, on a random input, it's hard to go back. And here is the whole problem of password hashing. That is that hash functions are easy to compute and hard to invert, but they're hard to invert on random inputs. They're not necessarily hard to invert if the input is of low entropy. Why is that? Because of course, given the hash of a password or given the hash of any value, an attacker can simply do brute force on the value itself to verify its guess. So if I give you a hash of some value x, you can try all possible values for x and hash them until you find a match with the original hash, and then you know that your guess will be correct. So as we have discussed, hash passwords are secrets with weak entropy. So they're short, they're not chosen at random, and therefore it's not very hard for an adversary, given to guess or to have a meaningful guess of the password. And if it's easy for the adversary to check their guess of the password, then this might be a problem if the password hashes leak. This is why this is a bit of a long tangent, and we're going back to this, but this is to justify why when we talk about hashing of passwords, we don't use the hash functions that we discussed in the week on authenticity. So we don't use SHA, we don't use SHA-2, we don't use SHA-3, but we use specific hash functions which have been designed for password hashing. Those are things like PBKDF or bcrypt or scrypt, which are functions which have been explicitly designed for the purpose of password hashing. And we're going to talk more about what this exactly means. So as I was saying, the server side will not store the password in the plain text, but will store the pair U, where they use the username of the user, and H, where the H is the hash, the one-way function, the hash function applied on the password, and then store this H. So clearly now at login, what happens is that the server receives the username. So I'm Claudio, and here's my password. So the user sends this information to the server, and the server will deny access to the user unless the H which was stored by the server is equal to F applied to the new password which is being input. So using password hashes doesn't mean that the server doesn't get to see the password. Of course, the server sees the password every time you send the password, and every time you log in, the server gets to see your password. But this means that the password is never stored in plain text on long-term storage, which means that if an attacker has access to the server, to the storage of the server, so where this file is stored, where the file with all the user's name and the passwords are stored, the attacker will not be able to immediately see all the passwords, but will only see the hashes. Of course, an adversary who has online access with corrupting the server will see the password, because when you log in, you send the password. But an adversary that only has access to the long-term storage of the server will not see the password, will only see the hashes of the passwords, and hopefully this will make life a little bit harder to find the user's password. So let's see how hard will this be. So first of all, let's you might have the objection that is, but if I cannot trust the server to store the passwords correctly, I mean, why would I store the server? Why would I trust the server with anything else, right? I mean, if this is your bank, or if this is the tax authority, I mean, if you cannot trust them to store your password securely, I mean, why would you trust them with other things? Unfortunately, I mean, there are technological reasons for why it's surprisingly easy to get hold of the password hashes. I mean, sometimes this is simply a feature. For instance, there are protocols like the LDAP protocol, which allow different services to share the same password across different services. So think, for instance, about your user experience at Aarhus University. There are many different services that you use. And for all these different services, you use the same password. So you use the same password when you use your for your mail address, which is Microsoft Outlook service. You use the same password on Blackboard when you log in and check what's happening for the different courses. You're also using the same password when you log in to EduRoam, and use the same password when you log in probably to different services. So all these different services need to talk to each other. So you need to assume that there is some way for these services to verify across different services that the password is the same. And so in some protocols, like in LDAP, it would simply easy for all of these different services to share. I mean, the way this is achieved is for all these different services to share the hashes of the passwords. So the hashes of the password are considered a non-sensitive piece of information, which is simply accessible from within the system. This is can also happen by design. For instance, in the Unix operating system, different users are sharing the same. It's a multi-user system where different users live on the same system, and different users on the same system all have access to the same password file. So all users can see the hashes of the passwords. Sometimes the password hashes leak because of simply leaks. I mean, someone is attacked the system, and therefore a big chunk of some database leaks or some password file leaks. This has happened to Yahoo. This has happened to eBay. This has happened to Adobe. And if you've never done it, there is this website, Ever Been Pwned, which is a project which collects all of these leaks. And they have this huge database of leaked passwords. And you can go there and you can download a database of hash passwords which have leaked from all of these services. And therefore, it's very important to ask the question, how hard it is to recover the password from the hash of the password or from the F of PW. And as we have discussed, the F is a one-way function, meaning that it's hard to invert, meaning that there is no easy procedure from going from FPV to PW. But of course, if you can guess, if you have a guess at the value PW and you know the value FPW, then it's easy to compute, to apply the function on PW and check whether this is the correct guess. So this means that password hashing is a bit different than regular hashing, and we need to use some extra precaution. So a very common precaution is salt. So salt or salting is the practice of storing the hash of the password together with some value, some random value s, known as the salt. So when you hash the password, you hash the password together with s the salt. So the salt is stored together with the username and the hash in the password file, meaning that when the server is verifying, so the user doesn't need to store the salt. The user simply will send the password again to the server, and the server will hash the password together with the salt and verify if this is equal to H. So clearly, this doesn't make it harder to attack a single user. I mean, if there is a single user in the file, and if you want to brute force the password for this particular user, you can simply do so because the salt is public. But the use of the salt helps for security in two different ways. The first one is that if two users have the same password, now they get different H's. So when the attacker gets the password file, they will not immediately be able to see if two users share the same password. And then, of course, I mean, this should not happen. So this is not the main advantage, but the main advantage is that now the attacker has to do work per user. So I mean, if you're not using the salt, now the attacker can simply try to hash all different passwords. For instance, all password in a dictionary, and then verify and then check whether any of these password any of his guess was correct for any user in the system, because the adversary can compute f of pw and then check whether there is any f of pw in this file is equal to the one that they achieved. But if you use the salt, now the adversary needs to hash the same password for every possible value of the salt in the user file. So the work that the adversary has to do suddenly gets multiplied by the number of users of the system. So in other words, adding the salt makes the work of the adversary. If you don't use the salt, the work that the adversary has to do to break into any user in the system doesn't grow with the number of users in the system. If you use salt, then the adversary has to to brute force the passwords of the users one by one, so the adversary doesn't gain any advantage by a system having more users. The other big advantage is that if the function f is public knowledge, so I mean typically we assume that the adversary knows the system, so the adversary knows what function is being used, and I mean as I was telling you before, there are the hash function that we use for password hashing are few and known. So without the salt, the user could, the adversary could simply at home do pre-computation. So the adversary could pre-compute the hash of lots of passwords, and then when they attack the system, they would have an easier time. Whereas if you use salt, again, the adversary has to do work which depends on the salt and therefore depends on each user of the system. The other countermeasure, or the other good practice that we have for making the life of the adversary harder when they try to steal the password on the server side, is to make the hashing slow on purpose. And here we're talking about moderately slow. I mean, we still want the hash function to be easy to compute and hard to invert, and we're just changing the definition of easy to compute from going from instance to being like maybe 1,000 times or 1,000,000 times slower. So something which is still acceptable from the user experience point of view, but which will make the life of the adversary harder by limiting how many tries per second the adversary can make. A naive solution would be, for instance, using the SHA, is to, instead of hashing the value directly, to hash the value and then to hash the hash of the value and then to hash the hash of the value and then to hash the hash of the value, for instance, 1,000 times or something like that. So this will slow down the adversary by a factor of 1,000. This is to give you an example of how this can be done, but the better solution, if you have to do this in practice, is to use a dedicated password hashing, such as bcrypt, scrypt, or pbkdf. So as a summary on password security, So passwords are often the weakest link in the cryptographic chain. And the way of improving security is to either help or educate the users in choosing better passwords. Avoiding password reuse prevents social engineering. A very effective measure is to limit the number of guesses that the adversary can do per second. This can be both do online in online systems where you simply program your system to say if the password was incorrect, then wait 3 seconds or wait 5 seconds before the user can input a new password. Or it can also be done in offline settings, so where the adversary, for instance, has stolen a password file, and you can do this by using things like salt or slow hashes. It's always very important to make sure the passwords are stored securely, so not in plain text. And in the book, there are a few more comments about things like password verification with secret salt, which is a variant of the salt that we've seen before, but where simply you don't store the salt together with the hash of the password, and you have 2 different servers, one that stores the password file, one that stores the salt, and the one that stores the salt is responsible to do the hashes. By doing so, you force the adversary to break into more than one machine in order to be able to steal the entire file. This is a very common design pattern in security. So by sharing, by spreading the secrets among different servers, you require the adversary to do more work to break the system. Something else you can read about in the book is password-based encryption, which is, for instance, what you can do when most file systems allow you to encrypt either a file or a drive. And this is typically done using a password. Now, a password is not an AES key, so how can you use a password to encrypt? So again, you can hash the password using hash functions like the one we described in the slides, and then use the hash of the function, the hash of the password as a key for an encryption algorithm like AES. And then we also have a few words about password managers, which are an increasingly popular solution for users to keep track of all the passwords. If you tell users not to reuse passwords across different services, then they have to store a large number of passwords in the head, which is, of course, very hard for them. So a solution is to use password managers, which are software that store passwords for you. So typically, you only have to store one strong password known as the master password, and then you encrypt all of your other passwords based on the master password. And this can be an efficient solution to let users have different passwords on every website they visit, and where all the passwords that they use for every website are generated uniformly at random, since the software generates them for the user, and where the user only needs to remember one strong password. And of course, this has advantages, but also has drawbacks, because now there is only one password, and now you have all your eggs in one basket. So I mean, if the adversary can break the master password, then they suddenly have access to all of your passwords. And of course, typically, most password managers, I mean, there are password managers that live in your browser on your machine, where the storage is only local, but the most common password managers are online, and they store the password, the encrypted passwords also on some cloud storage service, which means that those are now suddenly very attractive targets for attackers. But you can read more about in the book. Something else we should talk about a little bit is hardware. So an alternative or supplement to passwords can be hardware. Instead of the secret being something now the secret is something you have, and hardware can make it much harder, even if not impossible, to steal secrets. For instance, your Dancork is an example of a secure hardware. Inside the chip in your car, there is a key, and stealing the key from this chip is much harder than stealing your password or stealing your PIN code. Typically, it needs for someone to steal the key from the chip would require to have access, physical access to the card, destroy the card, and in some cases destroy the hardware, or in some cases it would be even impossible to steal the key from the device, depending on the kind of hardware you're using. In any case, it makes it much harder to copy the secrets than using passwords or the secrets that you know. So a good example of this again is magnetic stripe versus chip card. So in the old days, credit cards they were used by striping them by striping the magnetic stripe in the reader, and this essentially meant that there was a secret written on the stripe, and when you use your card, the secret is read by the reader and sent. It was very easy to steal this code, because I mean, every time you were reading, every time you were inserting your card in a reader, the reader would read your code. So essentially, every shop that where you ever use your card could potentially steal your credit card, and credit card fraud was very common. On the other hand, chips are when now we use cards with chip cards with chips on them. These chips instead are now essentially computers who are not simply giving away a secret, but they're like running protocols with the reader, and therefore the key which is stored inside the chip cannot be as easily stolen. Of course, not all hardware is secure, and there have been lots of attacks against all sorts of hardware token, car keys, hardware tokens to open garage or other doors. And there is a very interesting and entertaining tutorial, and there is a link at the end of the slides. And if you're interested in hardware security, you might want to watch this very entertaining talk by Timo Kasper, who is a German researcher who has done a lot of research in the security of hardware tokens. There can be a lot of issues with the hardware tokens, including side channels. So side channels are ways in which secrets can leak from a device, and these can be very many different kind of. There are many different kind of side channels. Typically, side channels have to do with things like the time it takes. Side channels are a way for adversary to learn about a secret by measuring something about the computation which is happening. It can be measuring the time that it takes for some computation to happen, or it can be measuring the power consumption that some computation requires, or it can be by measuring some electromagnetic field which computation induces. So some very simple example of side channel could be, imagine some piece of code that says that that looks at some secret and says maybe there is a secret which is a single bit, and now the code says if this bit is 0, do something, and maybe this something is something which is very heavily computational, so it takes a lot of time, and instead if the bit is 1, do nothing. So if you write your code like this, and someone can measure the time it takes for the computation to finish, they will be able, by measuring the time it takes for the computation to finish, to see whether the secret bit was 0 or 1. Now repeat this for something that happens for every bit of the secret, and now the adversary suddenly can read the bits of your secret key by looking at the time it takes to do a computation. So imagine, for instance, an algorithm that checks if a password is correct or not. Imagine an algorithm that, imagine for a second that you're storing the password in plain text on the server. You should not be doing that. And imagine that the algorithm the function you write to check if the password is that is being input by the user is the same as the one which was stored. And imagine that this algorithm does the following thing. It says, it checks the first character of the password input by the user, and checks if the first character is equal to the first character of the password stored. If the 2 characters are equal, proceed to the next character, otherwise reject. So now the time it takes to run this function depends on which position of the password, or which character in the password was wrong or right, which means that it's much easier to brute force the password by doing a character by character brute force than if you were checking the password all at once. So this is an example, a very simple example of a side channel. A more complex example of a side channel is by looking at the power consumption. So if you, for instance, if you in the week on confidentiality and authenticity, we talked about the RSA function. So in RSA, the decryption or the signing process uses an exponentiation by a secret exponent, and we discussed how doing exponentiation of for long values. This is something that is typically done by using by looking at this at the secret exponent bit by bit and using this kind of square and add algorithms. A trivial implementation of such an algorithm would heavily depend on the bits of the secret key, and therefore by measuring the timing or the power consumption of the device which is performing this computation, then it will be easy, or it will be easier for an adversary to learn the bits of the secret key. And the fact that the adversary can measure the time it takes to the computation or the power consumption or the power that is consumed by doing some computation is not unrealistic. So when you insert your credit card into a device, the credit card is being powered by the device which is running the protocol with the credit card. So the reader, a malicious reader, would be able to read and to have information about the power consumption of your credit card. Of course, measuring the power consumption is much harder if you're attacking someone who's on the internet and sitting, miles or thousands of kilometers away from you. But it's not very hard when you're measuring, when you're attacking a credit card which is in a device which was designed by the attacker. In the same way, measuring the time it takes to do some computation might be hard if someone is, if you're interacting with someone who is on the other side of the globe, because then the delays in the communication or in the network traffic might make it very hard for the attacker to measure the timing that it takes to do some computation. But if you're attacking someone who is on the same network as you, then these attacks might be much easier. Another issue with the hardware is that the user, the way that the hardware token interacts with the user might make it easier or harder for the attacker to break the security. So imagine there are hardware tokens that you can use, that you can buy online, that you can maybe plug into your machine, and that can do operations for you. But now the question is, and then maybe to approve the operation, you have to attach some button on the hardware token. So this makes sure, for instance, that your machine, if your machine is infected, they can just run anything they want with the hardware token. The user needs to push some button for something to happen. But if the hardware token doesn't have a display, then the user will only be able to say, yes, I approve a transaction, but the user doesn't know which transaction is being approved. As a silly example, imagine that you want to approve a payment of 100 krona, but you're running your machine, your laptop is running some malicious software, and instead it sends to the hardware token a transaction which is of 100,000 krona to approve. Now, if you cannot look at the amount, if the hardware token doesn't show you the amount on a display, then you're only approving a transaction. You don't know which transaction you're approving. So in some sense, mobile phones are hardware token that we're using these days, and you have experience using hardware tokens. For instance, the NemID app, which is running on your phone, if you're using the app, that is in some sense some hardware token. So something that stores a key in a storage which is hard to use, which is hard to steal from your phone, and that you're interacting with. So when we talk about hardware, we're talking about hardware in a broad sense. And I mean, hardware tokens are commonly used and especially your phone is very commonly used for what is known as two-factor authentication, which is a way of combining something that you know, a password, with something that you have, so a hardware. Example of two-factor authentications that you can use that you might have used in your daily life are SMS or authenticator apps or hardware tokens or the good old NemID paper card. So SMS is simply the idea that when you do a transaction with someone, when you're interacting with someone on the web, to make sure that you're really where you're claiming you are, they also send you an SMS on your phone. So now if the adversary wants to attack you, it's not enough to steal your password. They need to steal your password and your mobile phone. Unfortunately, SMS security is not as good as you might want to. So SMS are not the best. I mean, they provide a meaningful level of security if you're depending on your threat model. So if your threat model is someone that wants to steal 50 krona from you and buy a pizza online instead of you, then SMSs are probably a good enough tool for two-factor authentication. But if your threat model is something different and maybe involves nation states or secret services, then SMS is not are not the best tool for two-factor authentication. So another tool are authenticator apps, as I was mentioning before. NemID is a classical example of an authenticator app. An authenticator app essentially is just an hardware token that runs on your phone. Example of authenticator apps are, again, NemID, but also Facebook or Google are running authenticator apps on your phone. An authenticator app is essentially something that stores a key, a secret key on your phone, and then can be used to generate one-time passwords or one-time codes that can be used to authenticate some transactions. And the good old NemID paper card essentially was also an authenticator app or an hardware token where the token were simply where the codes were just pre-printed on the card. The way most of these things work is using a concept known as one-time passwords. And a very essentially what a one-time password is, in a very simplified way, is simply a way of computing a MAC on some challenge value using a secret key, which is only known by your authenticator app and the server side. So your NemID app contains some key, and the server side also contains the same key, so that there is a way of verifying that the code that comes from your app is the same, can be verified at the server side. So this challenge can either be a random number which is being sent to you and that you have to compute the challenge in real time, or it can be simply the time. So of course there are pros and cons on both using a random challenge or the time. We discussed some similar issues back when we were talking about authenticity, when we were talking about replay attacks, and the same considerations apply here. So if you're using the time as a challenge, then you need to have some kind of synchronization between your authenticator app and the service that you're authenticated onto. And if you've used, for instance, I mean, many authenticator apps, they have this, they show you a code, and then there is some counter that says this code is only valid for the next minute or so. And this interval that they've chosen, the minute, is a trade-off between having an interval which is large enough so that the user can read the code, type it into the machine, and being sent. And of course, it should not be too large so that the attacker can try to brute force the code in that period of time. Using random codes instead, or random challenge code which are being sent to you on the fly and that you have to reply to, require network communication between the server side and the authenticator app. So those can be used, but they require, for instance, that you have an internet connection. Other possible issues that you have, even if you're using two-factor authentication, you still have the problem of real-time phishing. So it might be that an attacker is trying to log in on your behalf on some service. They get some request that they forward to you, and then you forward to them the code, and then they can forward back to the the service on which they're attacking, pretending to be you. So to make the life of the adversary harder in this real-time phishing, it is often the case that the context of the transaction is added to this challenge. So you might have experienced that while a few years back, when you were getting, if you were getting one of these codes by SMS to authenticate some credit card transaction, you would only get the code, or maybe you were getting you were doing two-factor authentication from Google, you will only get like a code in your SMS. These days, increasingly, services are not only sending the code, but are also sending information about the context of the transaction. So, for instance, by SMS, when you're authenticating a credit card transaction using two-factor authentication, you will get an SMS that says, here is the code that you should input for the transaction of 500 krona on the website, shop.dk. In this way, they use that as a way of knowing whether they're being real-time phished or not. This, of course, also has there are pros and cons with everything. The more information you write in the SMS about the context of the transaction, the more the privacy of the user is being affected, because now the information about the transaction is being sent via SMS, which is not a very secure channel. Again, user interface is very important. I mean, the information that you show to the user when you ask the user to input this code for two-factor authentication can play a role. Other kind of hardware is tamper-proof hardware, or also tamper-resistant hardware or tamper-evident hardware. Those are all different kind of hardwares where it should be hard or at least evident if an attacker has tampered with the hardware, meaning that if the attacker tries to extract the key from the device, either the device should simply destroy itself, or the user should be somewhat notified that this has happened. So examples of tamper-proof hardware are, for instance, the IBM 4758 card, which is shown here in this picture. And this is simply a card which, of course, this looks like something that belongs in a museum. So some kind of physical hardware device that you can plug into your motherboard, and where a key is, and where a key lives inside this box, and this box is built in such a way that it detects whether it's being attacked, and it does so by, for instance, detecting whether the temperature is of the card is changing, or whether there is something is happening to the card which is not considered normal by the card itself. And if that's detected, then the card would simply destroy the secret. So this, of course, requires the card to have also some onboard power. So the card would not only be powered by the device it's being run on, but also has some power source inside the card itself. And again, there are many variants on this kind of devices. You have tamper-proof hardware, tamper-evident hardware, tamper-resistant hardware, and this kind of hardware is increasingly getting into our everyday devices. So most modern computers come with something known as a trusted computing platform, which is a platform which can perform cryptographic operation in a trusted environment where it's hard for the adversary to have access. Okay, so the final thing we wanted to talk about today are biometrics. So biometrics are something that you are, as opposed to a password, which was something you knew, and hardware, which is something you have. Example of common biometrics are your face, your fingerprint, your voice, your iris, and many other things. And I mean, these days, I think most of you are used to use face or fingerprint to unlock your phone. And of course, the main advantage of biometrics is that there is nothing that you need to remember. And they're also very convenient, because typically typing a long password is much more cumbersome for the user than simply look at your phone or put your finger on your phone. Of course, there are a lot of cons for biometrics. mean, there are cons which have to do with the user experience. If it's winter, you're wearing gloves, the fingerprint is not a very good solution. If there is a corona outbreak around the planet and you're wearing a mask, then Face ID is not the most easy software to use. So there are some issues from the user experience point of view, but also, of course, security concerns about biometrics. So one major concern is that biometrics cannot be revoked. If your password is stolen, you can change your password. If you think that that your password has been stolen, you can change password. You can't change your fingerprints. There are issues with privacy. I mean, if you use many different services and you don't want the services to be able to link your identity across the different services, you can simply choose a new username and a new password, and there you go. I mean, this is a fresh account, and these accounts are unlinked. But if you use your fingerprint across different services, all these services will store your fingerprint, and they will be able to link you and also link you to their real identity. And then finally, I mean, any system which uses biometric will have to be fuzzy in the sense that you need a balance between false positive and false negative. None of the biometrics that are listed here are constant. Your face changes over time, simply because of lighting condition or the way you woke up, on how long it is since you have shaved, how much makeup you're wearing. So your face changes, your fingerprint changes because your finger might be sweaty, or you might be you might have rotating the finger slightly, or things like that. So any such a system must allow for some tolerance. So if it system based on password, they only accept the right password and nothing else. A system based on biometrics must accept also biometrics with some degree of error. So you need to have this balance between accepting false positive, accepting being tolerant, and accepting slightly perturbed or noisy features, and not being too tolerant because that would allow the adversary to attack the system. So there is a bit more in the book, but pretty much this is all I wanted to say about biometrics. If you wanted to know more, here there are some of the links about things that I referred to in this video. And this was all for me for the course. So good luck from now on, and see you at the exam. Bye.